Okay, so, yeah, again, so thanks for coming. So just one quick thing. So this was given to me by someone in the audience. Yep, okay, so well, this is, what does XKCD mean? Okay, XKCD is a nerd comic on the internet. If you don't know it, I encourage you to go look it up, XKCD. So, calling the Ackermann function with Graham's number is the argument just to horrify mathematicians. And hopefully that doesn't mean anything to you at the moment. But by the end of the talk, hopefully at least it will make some sense. Okay, so there we go. So that's a preface. So this is, yeah, really big numbers. That's what we're talking about. Let me put this thing on. Really big numbers. Okay, I'm Anthony Mays, and so I work here in the department, Department of Maths and Stats, or the School of Maths and Stats, sorry. My boss isn't here, good. And that's also, I also work for the Australian Research Council Centre of Excellence for Mathematical and Statistical Frontiers. Yes. And so they're supporting this event as well. Okay, so, and this is all part of Science Festival. Great. So let's talk about really big numbers. So let's start at the beginning, like the song did, 0. Is 0 a big number? No. Okay, good. All right. Excellent. Let's go. Is 1 a big number? No? It's bigger than 0, good. Okay, and if we're doing probability, then 1 is like the most you can ever have, right? I mean, a probability of 1 is like 100%. It's guaranteed to happen, okay? And also, we can think about, we've got 1, and between 0 and 1, how many numbers are there? Infinity, right? There's an infinite number of numbers between 0 and 1. So, because I could have like a half, or I can have a quarter, or a third, or an eighth, or, you know, any of these little fractions in the middle. But 1's really not very big, is it? No, who cares about 1? Let's move on. Okay, so here we go. Here's a picture of my hand. All right, that's actually my hand. So 5 is the biggest number we can count to on my hand. All right, great. 5. There's 5 digits there. 20 is the biggest number. So okay, here's both hands, and there's my feet. Yeah, a little bit of a problem this morning, but anyway, no problem. I got my shoes on. 20 is the biggest number with both hands and both feet. And if, okay, we can count higher. If we have a whole bunch of hands, a whole bunch of feet, that looks like something like 100 hands and maybe 100 toes, 100 fingers and 100 toes. All right, but that's okay. We can all do that, right? We've more or less known these numbers for a little while. So let's step it up a little bit. What's the population of Melbourne, roughly? 4 million something. Is that... Okay, not billion. That's getting a little bit too far. But... that's it, 4.641636. Okay, that's how many people exactly that lived in Melbourne in the 2016 census. Okay, exactly that number. Population of Australia, roughly? 23.4 million. Whoa. Okay. Stop looking at the sheet. Okay, we shouldn't have given you the sheet. All right. Whew, yeah, I was about to give you the clicker. Okay, so this is exactly 23,401,892, okay, in the 2016 census. Population of India, okay, there we go, and the population of China. And again, these numbers are exact, of course, right? And I looked up these numbers here at exactly 11 o'clock at that time, and 2 minutes later, I looked up the population of China, okay, and then... a few minutes after that, I looked up the world population, and it was very handy. You see these websites here. This is the Chinese government website. It tells you exactly how many people there are. And this tells you how many people there are in the world. It's the Indian site. Okay? So does everybody believe those numbers? No? Nobody believes them? Okay, all right. So there might actually be some question about the accuracy of those numbers, and that's going to be a theme of the talk. How accurate are these big numbers? Okay, but we may need some help. Okay, so I don't necessarily want to write these things out every time, okay? I don't want to have to say that. So I found this cool thing on the old internet. And so if I type in the world population, which is 7528102,921, and I don't want to have to remember how to say it, this will tell me. That's 7,528,102,921. Okay, cool. Easy. All right, but let's get some bigger numbers, right? I mean, this is just the number of people on the planet. That's no big deal. Age of the universe. All right, now, okay, it's written on the sheet. I'm not going to ask you guys any more questions. Roughly, you know, getting on 14 billion years. All right, estimated. Okay, we don't have an exact number for this one, not like the exact number of people on the face of the planet. The age of the universe in seconds? All right, well, because we don't typically measure things in years in science, we have a standardized set of units, okay, in seconds. We don't use years. So how do I calculate that? Well, I need to know how many seconds there are in 1 year. So we have 365.24 days in the year, and each day consists of 24 hours. And each hour has 60 minutes, and each minute has 60 seconds. Okay, so if I multiply all of those numbers together, I'm going to end up getting the number of seconds in 1 year. Okay, and so that should be written right there. 31,557,600. Now, that's the number of seconds in 1 year, but I want to know the number of seconds in this many years. So what I have to do is I have to multiply those numbers together. Okay? And of course, I did this in my head just now, and there it is. Okay? Oh, no, there it is. Oh, yeah. Sorry, I was out by 1. But there it is. Okay? So whatever that number is. Okay? And we can go back to our internet site, and it will tell us what it is. Okay, that's the age of the universe, pretty well, in seconds. Now, what about Avogadro's number, another big-ish number in science? Have people heard of this one? And I know there's at least some people who have. Yeah, okay, yep, a few hands, yep. Good. So Avogadro's number. This is more or less the number of, or it's defined, sorry, not more or less, it's defined as the number of carbon-12 atoms, the number of atoms in exactly 12 grams of pure carbon-12. And we denote carbon-12 by this 12C. And what does that mean? Carbon is the stuff that we're all made of. Okay, it's the stuff that's everywhere in all organic items. Okay, it's carbon. That's what makes up most stuff in us. Okay, carbon. And carbon-12 is this one given right here. It's the most common, most stable form of carbon. And how do I know what this is? Well, it's got 6 little protons in the middle. Okay, that's what the pluses are. That's the pluses. And that makes it carbon. And then the 12 comes about because I've also got 6 little neutrons, okay? And 6 plus 6 is 12. So we call this carbon-12. Now, if it was carbon-13, which also exists, then I would have an extra neutron there. And carbon-14, it would have 2 extra neutrons and so on. Okay, so just for the definition of what we want for Avogadro's number, we want this atom here. All right, and we want to know exactly how many there are. So we need to start counting. Okay, yeah, there's some, okay? There's quite a large number. But I found another representation of it, okay? This thing here is called the pink star diamond, okay? And it was discovered in 1999, and it weighs almost exactly 12 grams, okay? And it sold earlier this year for $90 million. So if we divide that through, if we divide 90 million by Avogadro's number, then we know exactly how much each carbon atom is worth, okay? Good. All right, but Avogadro's number. So let's actually put a number on this thing. Here is a numerical approximation to this thing. That long number, okay? 602 something. But, as I said, it's an approximation. So it's somewhere between these two numbers, all right? Like I said, a theme of this is going to be about approximation. How accurately do we know certain things? So it's somewhere between 602 blah, 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 with this, 931, and 602 blah, 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 783. Okay, it's somewhere between those. But perhaps maybe what we should do is define, and this was a paper that I dug out. They said, well, perhaps we might want to actually define it to be exactly this number. Like define it, and it's this number cubed. I'm not going to go into why, but there's just this huge big number, and they said, well, let's just define it to be exactly this. But as it turns out, this number is not between those two numbers, so that's not going to be much use. So anyway, Avogadro's number is a notoriously difficult thing to define because we define it in terms of the gram, which is defined in terms of the kilogram, but the kilogram keeps changing. I don't know if you know this, but the kilogram is defined as the weight of the mass, technically, of a platinum cylinder sitting somewhere in France, okay, a sphere. And it really is an actual sphere sitting in a vault in France. And they take it out periodically, weigh it, and they check it. But each time you touch this thing or clean it or breathe on it, you change the weight of it, all right? And so that's why this Avogadro's number is not perfectly defined. So we're still working on making that perfectly defined, and I think we're not too far away. I think within the next couple of years we will have a very accurate, very precise definition of what it is. But anyway, not at the moment. But let's talk about big numbers, right? We're going to talk about really big numbers. These are big-ish, right? But I mean, still, it's a ring, a relatively expensive ring, but that's it. It's just the number of atoms in there. So what have we got here? We've got the age of the universe in seconds, and we've got Avogadro's number. Which one of those numbers is bigger? Avogadro? Yeah, most people say yes. Now, why? How do we know? Just by looking at them. It has more numbers, yeah, okay. And so which numbers can we look at that will really tell us that's making it bigger? The zeros, right? If we have a look at all these zeros, this one's got what? 8 zeros, and this one's got 3, 6, 9, 12, 14. Okay, so there's a lot more zeros here. So this, if this was in your bank, you'd be much richer than this guy, okay? Still, I would, you know, if anyone has that to lend me, I'll still take it. So Avogadro's number is much, much bigger. And how do we know, right? It's the number of zeros. So really, if let's just say there wasn't just this many zeros, let's say there was 10,000 zeros. And then I had another number that had 14,000 zeros. Just looking at them on a page, it might be difficult to tell. So what we really want is we want a new system for writing down big numbers. And so that's what we're going to do, right? We're going to shift, and we're going to look at something called multiplication. Okay, hopefully, have you guys all seen this now? Yeah, you guys, you know how to multiply two numbers? Yeah? Okay, so 9 times 9 then, what is it? 81. Okay, it's 81. What's 9 times 9 times 9? 700, yeah, okay, all right. So, yes, it's that one. 729, 9 times 9 times 9, 561, 9 times 9 times 9 times 9, that one. Now here I've got 9 nines. That's that number up there, 387,420, 489. And, oh, where are we going? So what I'm going to do now is, I can write these down, but I'm using up a whole lot of ink, well, I mean electric ink, to write down all these crosses and all the nines. So why don't I just record how many nines there are? Okay, instead of writing 9 times 9, I'm just going to write 9 with a 2 above it. And that says 9 times 9, all right, because there are 2 9s. So that's what that is. It says just take that, and so 9 squared, 9 to the power of 2, is equal to 81. And here I've got 3 9s, so I just write 9 to the power of 3, and that's 9 cubed. 9 to the power of 4, because there's 4 9s. 9 to the power of 5, and 9 to the power of 9. So that gives me this. So what do I care about that? Why have I done this? It's because if I look at this, there's what? 1, 2, 3, there's 9 digits in this thing. So I have to write down 9 digits. But here, I can do this in a much more compact form with just 2 digits. If I just write 9 with a 9 just above it, it makes this big, long number here. So then what's to stop me making this number here, this power, the exponent, that's where this word comes from, what's to stop me from making this bigger? And that is nothing. Why don't I just try 9 to the power of 99 and see what happens? Okay? How big do you think it is? Big? Yeah, it's pretty big. Yeah. Okay, so it's that number right there. Okay, that's 9 to the power of 99. So in order to write that down in a nice compact form, I only needed 3 little numbers, just 999. Okay, so that makes a really, really big number. So that allows us to write down this giant number that if I was just going to write that down, it would take me a long time. I'm just going to write it down like that. Okay, so how are we going? Are we okay with this? Yeah, so taking the power is going to make things a lot easier. All right. Oh, cool. Okay, so what we'll do is we'll make our lives even simpler. If there's one thing scientists love to do, particularly mathematicians, it's make our lives simpler. It might make your life more difficult, but it's going to make our life more easier. So 10 times 10, all right? That's 10 squared. So we just talked about that. There's two 10s. So I just raise it to the power of 2. And that's equal to, what's 10 times 10? 100. Good. And what is 10 times 10 times 10? 1,000. Very good. And what is 10 times 10 times 10? 10,000. Next one. Okay, what's this one? That's 1 billion. Close. But yeah, if we go back and listen to the song, it's 1 billion. Close, though. And I mean that, it's actually close. We'll get to why it's close. Okay, so that's 10 to the 9. And what about this? Again, I wrote down 9 to the 99. What about 10 to the 100? Okay? It is one Google and it's on your sheet. Now I'm on top of it. I'm on top of it. And that looks like this thing here. Okay, so it's a 1 followed by 100 zeros. Now, why do I know it's a 1 followed by 100 zeros? Let's look at the pattern up here. I have 10 squared, 10 to the power of 2, and I have 2 zeros. If I have 10 cubed, 10 to the power of 3, I have 3 zeros. If I have 10 to the power of 5, then I have 5 zeros. And, this one here, 10 to the power of 9, I have 9 zeros. And then the same for the Google. So essentially, I can just shortcut this whole thing by saying I take 10 to the power of some number, and that number is the number of zeros. Okay, so that makes my life much simpler, because all I have to do is just write there how many zeros there are. I don't have to write every single zero down. I just know that that's how many there are. Okay, so this is going to really save us a lot of time. Okay, and a Google is also called, not going to put it in my machine, but if you put it in there, it's something like 1 trillion or something, some Latin-esque word that I just can't pronounce. Okay, but anyway, it's a very long, complicated word. That is a Google. All right, so exponential notation. So what we're really talking about, multiplying by 10. That's going to make our lives nice and easy. Okay, so let's try a little bit more complicated, and this is the sort of the heaviest part of the talk. Okay, if you get through this, then we'll be sweet, and then we'll get on to the really giant numbers. Okay, but just hang on to this bit. So if I take 2.1, okay, that's like 2.1, it's 2 and a little bit, and I multiply that by 10, I get 21. All right, so essentially all I do is I take that dot and I move it to the right. All right, if I multiply it by 10, I just move the decimal place to the right one spot. It gives me 21. Here I've got 35.8. I want to multiply that by 10. And that'll take that decimal point, move it 1 unit to the right. And that gives me 358. And if the decimal point is already as far on the right as possible, right? If I've already got 21 and there's a little decimal place here that I don't write in there. If it's already there, then if I multiply by 10, I just stick a 0 on the end, which is what we just did before. Okay? And the same here. I got 358. If I multiply that by 10, I get 3,580. Okay, like I said, this is sort of the heavy part, but we'll get there. And I can do this multiple times. So if I take 2.1 and I multiply it by 10 and multiply it by 10 again, I get 210. Right? I'm multiplying it by 100. And here I've got 35.8. I'm going to multiply that by 100. I get 3,580. So it's exactly what we did on the previous page. I'm just compressing everything, making it nice and simple. All right, now I can keep going. 35.8 multiplied by 10 by 10 by 10. So that's going to be, remember, 10 by 10 by 10 is 10 cubed. It's 10 to the power of 3. So that's what I've written here. So I'm going to multiply this number by this is an error. That should be a 4. Oh, I'm sorry about that. That should be a 4. I'll just quickly move on. And we'll do this one, and then we'll be correct. Okay, so this is for you guys to do. All right, so on your bit of paper, which you've got, your pen, I want you to write down what this number is. Okay, is everybody pretty happy with what they should do? Right, so I've got the decimal place here, so I need to move it to the right 5 times. What I need is a drink. Okay, hopefully you've had a good go at it. So what we've got is 548.98, and I've got a 5 here. So I'm going to move 548.98, and I'm going to move the decimal point 5 times to the left. So I move it here, and then to here, to the right. Did I say left? No, I didn't. I'm being recorded, and I'm sure I didn't make a mistake. Okay, yeah, that's right. Yeah, exactly. Okay, to the right. Thank you. And so I move it over here, but I need to move 3 more times. So that means I put an extra 3 digits on the end, 3 zeros on the end. Okay, so the number that I get left should look like that. It's 54898,000. Okay, so that should be the number that you get. Okay. So why do we do this? That's because this makes it very easy to multiply big numbers together, all right? So let's do another example. So what I've got here is 2.1 multiplied by all that stuff. So I have 2.1 times 10 to the 2, all right? That's what I've written up there. And I'm going to multiply that by 35.8 times 10 cubed. Okay, I'm going to multiply those 2 numbers together. Now let me just expand out the brackets, okay? If you remember your BODMAS or your BOMDAS, I'm just going to expand out the brackets. 2.1 times 10 times 10 times 35.8 times 10 times 10 times 10. Okay, and I went to all the effort of writing all of those numbers out. Okay, so I've got this. And all of these timeses, I can rearrange those however I like. I'm allowed to do that. It's a special word that we have called commutative, right? I can move these things around however I like. So I'm just going to move these ones up to the front. So I get a 2.1 multiplied by 35.8. This is the boring bit up the front here. The next bit, how many 10s do I have? I have a 1, 2, 3, 4, 5. So I can just write that. Okay? So I took the 2.1, I put it here. I took the 35.8 and I put it here. And I just put some brackets around it just to keep it away from everything else. And then I had 5 10s left over, which I wrote down here. Okay? So that gives me this one here. And then I go and calculate this, and of course I'll just do this in my head and I won't make any mistakes. Don't know my left from my right. Yeah, I get 75.18 times 10 to the 5. Okay? Now, this is the answer, which I have written up there. Okay. Now, you might say, okay, who cares? Fair enough. That's a good point, because I don't really care about that. All right? This number here, this 75.18, I don't really particularly care much about that. What I particularly care about is, you see this is 10 squared, and this is 10 cubed. What do I get in the end? I get a 10 to the 5. And that's 2 plus 3. And so really what I'm trying to do is make my life easier, because I don't really care that much about this number or this number. All I want to do is make things easy, and I just want to add the powers together. So I get 10 to the 5. Okay? And plus some extra stuff out the front that we'll worry about in a second. All right? But that's essentially what we're doing. Right? In order to understand these big numbers, this is the whole point, is that when I multiply these together, what I want to do is I want to add the powers together. All right? I got a 2, whoop, and I got a 3, and I add them together and I get 5. Okay. All right. Like I said, so we've done the hard bit. I'm just going to wind it backwards a bit. I'm just going to define what this thing called scientific notation is, and then we're all ready to go. So I'm just going to go backwards. I got 21, all right, and for some reason I just put the 0.0 on the end there. 21.0, and I can write that as 2.1 times 10, right? We've already talked about that. 358, da-da-da, I can write like this one here. We can do this multiple times, da-da-da-da. This is all getting a bit dull. But let's have a look here. 35,800, I can move the decimal place all the way to the left, yes, thank you, left. Or I can move the decimal place all the way to the left, and what I should do is keep track of how many decimal places I moved it. So I put this 4 up here, okay? So I take this, there's a decimal point here, I move it 1, 2, 3, 4 places to the left, and I get this number right here, okay? I just keep track of how many decimal places I moved it. All right, so try this one. Okay, so remember, I've got the decimal place over here. I need to move it as far to the left as possible, and then I just write times 10 to the power of whatever that was. Okay. Okay, so what we have is this number right here, which is, I'm going to put a comma in there, 54,898,000. And I have to move this decimal place 1, 2, 3, 4, 5, 6, 7. Did I get that right? 7? Yep, 7. Okay, I need to move my decimal place 7 points, I need to move my decimal point 7 places to the left. So I get 5.4898. And I've got all these zeros on the end, but whether I keep them or not, doesn't really matter. Okay, I can put the zeros there or not. 10 to the 7. Okay, so I move my decimal place as far to the left as I can, and just keep track of how many places I moved it. And I've got all these zeros that would be here. Keep them or not keep them, it's okay. This is not a test, okay? All right, so we're more or less on board, yeah? So if we can do this little bit, then you've understood what we call scientific notation, all right? And we call it scientific notation because it's extremely useful in science. If we're going to describe numbers, I mean, this number's not so bad, I can write that down. But if we're going to talk about Avogadro's number, I'm not going to write out the 23 digits every time. That's boring, okay? Scientific notation. So here we go. Have a crack at this one. And it should be on your sheet. I left some space, and I don't think I put the answer on there. No, I didn't. So have a look on your sheet. Let's see. Oh, no, it's not on your sheet. Is it on your sheet? Yes, it is on your sheet. On the back. Yep. So have a crack at doing this one. So firstly, convert it to the scientific notation, and then try to do the multiplication. I'm not going to write that out. Okay, so if you're having a bit of trouble, get started. I'll give you the first step. 9. Oh, there's the clock there. Okay. All right. The time doth march on, so we should probably keep moving. So did everybody write this bit down? Okay. 3 times 10 to the 7, which is 30 million, multiplied by 2 times 10 to the 12, which is 2 trillion? Yeah, 2 trillion. Okay, so I've written these two down. And so now all we have to do, remember, we add the powers. Okay, so like I said, we're going to make our life so easy. What is 7 plus 12? 7 plus 12 is? 19. Very good. Okay, so I know that this is going to have a to the 19. And out the front, I have a 3 times 2. So what's 3 times 2? 6. How easy is that? Okay, so if someone says to you, what is 30 million multiplied by 2 trillion? Then you just put it into scientific notation and it's very easy. It's just, well, that's obviously just 6 times 10 to the 19. And you'll sound very smart. Smarter than me, no doubt. Get your left and right correct. Okay. So, like I said, this wasn't originally going to be the point of this talk, but I found as I was going through it, we started getting to these numbers that were so ridiculously large that we can't possibly know every single digit of them. And so I thought, really, the point of big numbers is that near enough is sometimes, and in fact, usually, good enough. Right? We are interested in approximation. All right? So back to Avogadro's number. Looking at this number here, 6.02 times 10 to the 23, and 6.02 times 10 to the 23. Are those numbers, how different are those numbers? Do they look pretty similar to everybody? No? Okay, well, let's not be a stickler. So 6.02214 and 6.02214, I even include the 0. Up till that point, they're exactly the same, okay? Up to that point, they're exactly the same. They're only different in these last little decimal places. They're small. They're only like, yeah, what, 100 quadrillion or something? That's nothing. 100 quadrillion. It's between friends, there's nothing, okay? So really what we're talking about is it's somewhere in the middle there. But for a lot of purposes, it doesn't really matter what those ones are. I can just drop off most of those. In fact, when you're doing chemistry at school, most of the time, they'll just tell you to take 6.022. All right? They just say, plug that into your calculator. Don't do that. But 6.022 is often good enough for what we want. Okay? And this is the art and the science of approximation. And it is both an art and a science. It's an art because you need to know when you're interested in an approximation and when you can get away with an approximation and when you can't. And it's a science for how good your approximation is. Because if you want to actually know exactly how close yours is likely to be and what errors you have, then there really is a lot of statistics and a lot of probability that goes into that. So it is both an art and a science. And so let me give you a big fancy word that I've written here in bold, the order of magnitude. Now, doesn't that sound impressive? These two have exactly the same order of magnitude. And what does that mean? It means that number right there, okay, the 23. The order of magnitude of these two numbers is exactly the same. And then what we say is, well, they're equal up to an order of magnitude. And if you think I'm just making this up, go to the physics colloquium and every week someone will say this, okay? Order of magnitude is a very important thing because it gives you a rough idea of how close things are. If this was 10 to the 24 and this was 10 to the 23, then it differs by a factor of 10. So one would be 10 times bigger than the other. But if not, then the maximum difference is 10 times, okay? And that's not so bad, right? If I'm talking about something with 23 zeros stuck on the end, or 23 digits, and it's out by 10, near enough, okay? So that's what order of magnitude is really important, right? So go to school tomorrow and tell your teacher, well, it's an A up to an order of magnitude. It's cool. Okay, so here, to give you an example of how useful it can be, right? How many carbon-12 atoms are there? Let's just say, did we bring any of these pink star diamonds? No. Oh, we forgot them. Okay, sorry. Well, let's just say we had 21,354,543 of these pink star diamonds. That's just a number I made up, okay? It has no relevance whatsoever. But if I wanted to say, for some reason, how many carbon-12 atoms are there in all of those diamonds, well, I should probably do this approximately. I'm going to say 21,354,543 is approximately equal to 2 times 10 to the 7. All right, now why is that true? I'll just move my decimal place 1, 2, 3, 4, 5, 6, 7. And I'm going to forget about all those numbers. Just ignore them. So it's 2 times 10 to the 7. Closely. Right? Not too far, I think. And Avogadro's number, we look at it up here. I don't want to worry about all those numbers. They're boring. I'm just going to have 6 times 10 to the 23. And now I've got something very easy that we can calculate. What's 2 times 6? 12. And what is 7 plus 23? 30. Very good. You guys can do maths. It's very, very easy, right? We know pretty much how many there are. And up to the approximation, it's good enough. And let me show you. If you were to actually calculate this with the best approximation that we have to Avogadro's number and use this number exactly, this is the number that you get. Okay? Ignore all of these numbers here, and it's exactly the same as that one. So up to the order of magnitude, it's exactly the same. So I didn't need to go through all this effort, and sit down with my pencil and paper and my log tables or whatever. You wouldn't use log tables, but I would sit down and do these calculations. I could do this, and I got the computer to do it, and it gives me this number, but really, all I care about is something that's close enough, all right? Because once I say 12 point da-da-da-da, once you say the point, people stop listening anyway, am I right? Yeah, exactly. Okay, so let's get some bigger numbers. We've got the scientific notation under our belt now, all right? We know that we've got something raised to a power, and then when I multiply those two things together, all I do is I add the powers together. So what is pretty much the width of the universe? And I should have put inverted commas there. The width of the universe is not a very precisely defined term, but for what we're doing, it's near enough. Okay? You're getting a theme here? Near enough? Okay, good. Width of the universe. Pretty well 91 billion light years, okay? Well, what does that mean? These numbers are getting so ridiculously large that it's hard to put in the context of anything, right? I mean, we know there's 7 billion people on the planet, so if we had somewhere around 15 planet Earths and we lined all those people up, each one took up a light year, then we would get, these numbers are so ridiculously large that we really have trouble imagining them, okay? And these numbers, to say where we're going, are extremely small compared to where we're going to end up. So 91 billion light years. Okay, I'm just going to write that as 9.1 times 10 to the 10. All right, I'll just give you that one for free. And that's approximately 10 times 10 to the 10. 9 is 10, as far as I'm concerned. Yeah, tell your teachers that, right? 9 is 10. Now, okay, we have to write things in meters, okay, so I have to do a little bit of conversion here. There's roughly 10 times 10 to the 15 meters in every light year. That's a lot of meters, right? But again, don't even try to worry about visualizing it. Let's just think about the numbers here. We've just got a 10 and we've got a 15. If I'm going to figure this out, all I have to do is add the 10 and the 15. So the width of the universe is going to be 10 times 10, which is 100, and 10 plus 15, which is 25. Exactly. All right, so that is pretty much the width of the universe. And I've got an extra couple of zeros, so I'll move my decimal place 2 more points, and that gives me a 27. And there we go. All right, so does everybody kind of get the right idea? Yeah, it's that I'm just going to round it off and round this one off and do the multiplication, and it gives me a nice clean answer. And again, you do the calculation properly, you end up getting this number here. And 0.86 is pretty close to 1, I think, all right, for what we're doing. And so that's pretty close as well. So you get the right order of magnitude calculation without needing the complex calculations that you would need to do, you know, using a computer or, you know, by hand. But who does that anymore? So more approximations. How many atoms are there in the universe? Roughly 10 to the 70, 10 to the 80, right? I mean, again, the numbers are getting so ridiculous that what does that even mean? 10 to the 70, 10 to the 80. Well, right. So this number here, is this roughly 10 times as big as this number? No, because this is 70 and this is 80. That's 10 more, right? No? Okay. This is 10 orders of magnitude bigger than this one. So that tells you that this is, in fact, what is that? 10 billion. Yeah, this is 10 billion times bigger than this one. But again, physicists are like, nah, don't you worry about that. That's a pretty close approximation. Whether it's 1 or whether it's 10 billion, she'll be right. Okay? So, but, I mean, okay, so I'm being a little bit ridiculous. The difference between 1 and 10 billion, that's a big difference. The difference between 10 to the 70 and 10 to the 80, let's not stress about that between friends. It's okay. And then one more big number in physics. Here we go. An atom is roughly half a nanometer. Okay, that's a very small amount. We'll save the very small numbers for another talk. But let's say we fill up the universe with atoms. That's going to give us roughly 10 to the 111. Okay, so that's a 1 with 111 zeros after it, and that's a pretty big number. Okay, that's how many atoms we can fit in the universe, approximately. Okay, so let's go back to the big numbers. We talked a little bit about physics. Let's do some big numbers. So one Google, we talked about this thing before, right? And you guys have all heard of Google, the search engine, right? Google, yeah, you know how to like Google something instead of doing your homework? Yeah, Google, yeah. Okay, this is the original meaning of the word, right? Google, okay? And Google, the company, stole it and then, you know, changed the O and the L and for an LE and thought we wouldn't notice, but we did. So this is the original meaning of the word Google, okay? And it comes from a mathematician's nephew, apparently, that he asked him, the mathematician said to his nephew, what would you call this? And he said, well, it's a Google. So, and that's what it is. So now it's a Google. All right, so it's 1 times 10 to the 100. Now, what's 10 times a Google? Right? That gives me an extra 10. So all I have to do is add a 1 there. All right? You might have originally thought, well, what's 10 Google? I don't know. But it's just, I just add a 1, right? Because it's an extra 10. What's 100 times a Google? Well, now I add 2 10s. So I've got 102. But let's get really big. 1 times 10, now I'm going to put up the top, I want to have a Google zeros. All right, so remember a Google is this number here. It's a 1 with 100 zeros after it. Now what I'm going to do is take that number and make that many zeros. All right, does that kind of make sense? All right, so I've got a number that's this long, and then I take that many 10s and multiply them together to make a number pretty big. All right, so this is, and I got our ASEN's representative to check all these numbers, and there's exactly 100 here. Okay, so there's nothing, this one's right. And this we call a Googleplex. And this thing is a Google, it's a 1 with a Google number of zeros after it, and that is a very, very big number. Okay? Does it fit in the universe? You can't write it down because we don't have enough atoms, right? We only have roughly 10 to the 80, give or take 10 times 10 billion. But we don't have anywhere near enough to write this down. But remember I said if we filled the universe with atoms, we had somewhere around 10 to the 111. And that's cool, because this is only 10 to the 100. So that's cool, so no problem. Right, now you may not be following all these numbers, but the point is, this is the Googleplex. And in principle, in theory, if the universe was very different to what it is, we could write down a Google in the universe. So that's kind of boring, all right? What we want is we want numbers that are way too big to fit in the universe, like way too big. And that's where we're going next. But we need a new writing system, right? We've used the exponential. We've sort of flogged that thing to death. What we want is we want a new system. And this is what's called arrow notation. Okay, oh, hang on. We'll get to that in a second. Sorry. I'm going to take powers of powers. So remember that a Google was 10 to the 10. 10 to the 100. And that means I can write it like this. So let me just be precise about this. If I had... So remember, a Google was 10 to the 100. So if I want to write 10 to the power of a Google, then I would put the 10 down here. Oh, that should be... Yeah, I'm missing an extra 0 up the top. Okay. All right. I finished these slides only an hour ago, so sorry. So this is what the Googleplex should be, okay? It's 10 to the power of 10 to the power of 100. Okay, so that is a pretty big thing. And we're going to call this thing... Oh, okay, hang on. I'll tell you this bit first. So with well, it should be 7 digits. With 7 digits, we can write something that's pretty well the size of the universe, okay? 10 to the... a 1 with a Google zeros after it. If we were actually going to write that thing down, we'd have to take up a fair chunk of the universe to write it down. Okay, and we call this a tetration, right? And that's a pretty boring word, all right? What we're going to do is we're going to take power, like the power of the power of the power. A much better word is a power tower, okay? Because it's a tower, and it's got powers. It's awesome. Okay, so let's tidy the things up. Here's the arrows, okay? Just going to make things a little bit neater. So remember we had 6 times 6 equals 6 squared. And I'm just going to use an arrow to mean put that 2 above the 6. Right? That's what that means. Okay, so take the 2, put it at the top of the 6, and that's 6 squared. Here I've got 9 to the power of 4. So I'm going to use that arrow to mean take that 4, put it up the top of the 9. All right? And so one Google would be, that should be a 0, very sorry. That should be 10 arrow 100. Okay, it means put the 100 up the top. That is one arrow. But what's to stop us from putting more arrows? Now, that's the one thing, in order to make big numbers, you just do more of what you were doing. So here we go, let's make some power towers. So what the 2 arrow means is take the 2, right, and then make a tower of it, a power tower, with 3 of them, all right? So what I've said is take 3 number 2s and arrange them like this. Okay, I'll give you another example. Maybe it'll be a bit more clear. Here, I'm saying 5 arrow arrow 3 gives you 5 to the 5 to the 5. Okay? Right, because I want 3 5s. Okay, and that's a big number. This one here, 5 arrow arrow 4 says take 4 number 5s and arrange them like this. So put them in this tower power. Okay, the power tower. I'm getting all my hours mixed up. All right, so you put them up like this. And this is, again, a massive number. Okay, my computer couldn't calculate this one. So there we go. Okay, Googleplex. Oh, again, I'm missing zeros. Oof. Essentially, it should be a 10 to the 4. Let's not look at that one. Let's look at this one. Let's make the numbers really big. 10 arrow arrow 10. Take a 10, raise it to the power of 10, to the power of 10. Right? That is a ginormous number. Okay? That is nowhere near close to any universe that we possibly imagine can fit this thing. All right? This is a massive, massive number. Okay? Because remember, the Googleplex looks something like just this little thing. That's a toy. All right? I mean, there should be an extra 0, but who cares? 0. 0 is nothing. I'm going to raise that a whole bunch more times. Right? A Googleplex, but much, much, much bigger than that. Okay? So that's what our arrows are doing. So 2 arrows makes very big numbers. So with a 1 0 arrow arrow 1 0, what is that? 6 things. I can make this giant number, absolutely giant. Okay, so that's the big numbers. Now, where do they come from? Why do we care about them? This is where your other bit of paper comes in. All right? So you should all have a sheet that looks like this. And this is what we call Ramsey Theory. So what we're going to do is we're going to draw some dots. And then connect every dot with a line, all right, or an edge. And so if you look on your bit of paper, you should have a whole bunch of different dots arranged in various shapes, and every single one of the dots is connected with a line, and we call that an edge. Now, if every single point is connected to every other, this is what we call a complete graph. All right? It doesn't matter why we call that, it's just complete. You know, it's full of edges. And then we colour each edge either red or blue. That's going to be the game that we're going to play, okay? And I've done a few here. So what we're going to do, okay, the thing we might say is, okay, how many colourings are there? Let's go and colour our thing all in and see what we get. Okay, how many are there? So start at the top of your sheet. We have 2 dots connected by a line, okay? How many different ways are there that we can colour in those lines so that the graphs look different? Okay, so we have 2 dots and a line between them. Now, how many colours do I have? I have red and blue, but okay, if you don't have red and blue, you might have red and green. You might have green and black or something. Okay, you've got 2 colours. The line between them, I can either colour green or I can colour red. Okay? And so there should only be 2 possible ways to colour in these 2 ones at the very top, right? I can either have the line in the middle being blue or green, or it could be red. Okay, so there's only 2 possible ways to do that. Now it gets a little bit more complicated. So try colouring in the triangles. All right, try to find all the different possible ways to do it. And there's 8 of them, and you should have 8 triangles there. You know what to do? Okay. All right, I've just been told that the time is moving on, so we should probably keep going. But hopefully you were able to find that there were 8 different ways to colour them in. So here's one. I coloured these 2 edges green and this edge red. Okay, because there's 8 possible ones. And how do I know that there was 8? Why have I written this 2 to the 3 equals 8? Why is that there? Well, how many different choices did I have for each edge? So this edge here, how many different colours could I have chosen? 2, yeah. And how many different choices for this one? And for this one? Exactly. So I had 2 times 2 times 2, which is 2 cubed. And so that's the 8, okay? So now if we have 4 dots, if you look at your bit of paper, you count how many edges there are in there, inside the square. In this, yep, there's 6, exactly. And so for each one of those, I have 2 choices. So I have 64 possible ways to colour it in. And that's going to take a little while, and I didn't give you enough. What about the 5 dots? You should find that there are 10 edges, and that gives us 1,024 colourings. And that will take a long time as well. And 6 dots, well, okay, we're getting up to quite a lot. Take a long time to colour them all. So let's try one more little exercise that might be a little bit more interesting. Start with the 4, okay, with 4 points. And what I want you to do is try to colour it in so that you don't get a triangle. And I'll show you what I mean. So that you don't get a triangle. So I have these 4 here. If I try to colour this in and I say I draw like a red one here and a red one here, and I draw, say, a green one here and a green one here, and then a red one here, and then a green one here. I've made a little green triangle, okay? But I don't want to, I want to try to colour this in so that there isn't a green triangle. That's the thing. So can you colour in the 4 points so that there's no green triangle or red triangle? Okay, did anybody find one? Yeah? Okay. So there's an example. I'll just draw one right here. Oops, that's a triangle. So that's not going to work. So what about if I put that one across the middle there. Oops, I need to get my green. There we go. So that doesn't have a green triangle or a red triangle. Okay, everybody comfortable with that? Yeah, so I've got like some red box around the edge, but that's okay. And then I've got this one going here, and that one there, and that one there, but it doesn't form a triangle, because this is not a point. Okay, oh yeah, so, okay, I can see you guys were like, well, what? This is not one of the points, right? There's only 4 points, so we need to connect the points and make the triangle around there. Okay, so I can do that. And for 5 points, okay, yes, we are sort of running out of time, so I'll just give you a quick one for that one. It is possible to do the same thing with 5 points, but I want you to try the 6 points. Okay, so for the 5 points, I can do this. That one. And so that doesn't have a triangle in it. Okay? But what I want you to do is try the 6 one. Okay? I want you to see if you can draw, colour in all of the edges of the 6-sided thing, and see if you can form one without a blue or a red triangle.
Just between the points?
Yep, just between the points. Has anyone been able to draw one yet?
I think so.
Yeah? Okay. All right. Okay. All right. So this one is a trick question because it should not be possible. Okay? So it was possible for 3, it's possible for 4, it's possible for 5. It is not possible for 6. Okay? And why is that true? So we'll just do a little quick proof. If I was to draw, say, this point here, from each point, I have to have 5 ones coming out, right? I have to have 5 edges coming out of every point. Everybody agree with that? Right? Because I've got 5 points I have to connect it to. So, and I only have 2 colours, which means I must have one of the colours, right? So if I draw, say, red, green, red, green, red, one of the colours, there must be at least 3 of them. Okay, everybody happy with that, right? Because I have 5 edges, but only 2 colours. So that means I have to have a 3 and a 2, at least. I could have 4 and 1, or 5 and 0, but I have to have at least 3 of one of them. So what does that mean? So I look at the red ones here. That gives me 3 points where the red ends up. Now, if I connect any one of those with a red, that makes a triangle. So that's no good. So that means I have to connect all of those with green. But then, of course, I just made a green triangle. Okay, so there is no possible way to be able to create in a complete graph of 6 vertices. There's no possible way to avoid either a green or a red triangle. Okay, that's the point. Now you might say, okay, so what? Okay, this is what gets known as the Ramsey number 3-3, and it's the minimum number of points so that we have to have at least 1 blue or 1 red triangle. Okay? Now this might be starting to do your head in. I'm sorry. I know it's getting late. It's dinner time. Minimum number of points, which means that if I have 6 or more, right? If I have, say, 7 points or 25 points, 38 points, at Google points, I must find a red triangle or a blue triangle in there somewhere. Okay? I have to. That's what this means. And it's 6. And we just proved it was 6 because we showed that it wasn't 4, it wasn't 5, and it most definitely was 6, okay? So it had to be between 6, and therefore it was 6. Good. So R4-4. If we were to do the same trick again, what we would be looking for is now not looking for a triangle, but looking for a square, because we're looking for something with 4 edges on it, okay? We're looking for a little complete square in there. And it turns out that that number is 18.
Quadrilateral.
Sorry?
Actually, it's a quadrilateral, not a square.
Okay, fair enough. I will grant you that. Thank you very much. Yes, it is a quadrilateral. It is a 4-sided complete graph. Okay, complete graph on 4 vertices. So now what we're looking for is, okay, so a pentagon, is that okay? A complete pentagon, so it's a 5-sided polygon. So The R55. Now, why am I talking about this? It's because of this question mark. All right, that's the whole point of this talk. It is this question mark here. Look, it's easy to find triangles. We just did it. It's pretty easy to find squares, okay? Quadrilaterals. It is very, very difficult to find these pentagons. And let me show you. Paul Erdős, okay, who's a great mathematician. You may have heard of him, okay? He's certainly one of the more famous ones, certainly the most prolific one since Euler. He said this, more or less. It's an approximation to what he said. If aliens landed on Earth and said that they're going to destroy the Earth in 1 year unless we give them the number R55, so the Ramsey number, then we should all get together and work on it, and in a year we'll probably have it, we'll give it to the aliens and everything will be fine. If instead they said, give us R66, so now all we're looking for is a hexagon, okay? It's only a hexagon with all the little bits in the middle. If they said that, he said, well, we should just get everybody together and all build weapons to fight the aliens, because there is absolutely no chance we will be able to find this. And so let me tell you about this R55. The best estimate we have is it's somewhere between 43 and 48. Now, why is that difficult? Because how many colorings are there of the graph? Right? Remember we started out, the number of colorings of the triangle, there was 8 of those. The number of colorings of the quadrilateral with the things in the middle, there was 64 of those. 1,024 of the pentagram. How many colorings are there of the graph with 48 points? 2 to the 1128, which is too big. Okay, that's why the dots are there. But I can do a nice approximation. It's got roughly 340 digits in it. Okay, it's a big number. So let's just sit down and calculate it. So I got my desktop out and I asked it to calculate this. I've got a quad-core 4 gigahertz processor on my desktop. Takes roughly this long. Okay, is that a long time? How old is the universe? Not very old, okay? So that will take a very, very long time to go through these calculations and actually check them all. Okay, so that's why this is hard. Now, why do we care about Ramsey theory? It's important in communications and networks and all this sort of stuff. So that's why people actually calculate these things. So here we go. Here's the whole point of what we're doing. Graham's number. This was what was written on the XKCD joke that I showed up at the beginning. Graham's number. Here we are. 1980 Guinness Book of Records, the largest number ever used in a mathematical proof. And he was looking for, why did I start talking about Ramsey theory? He was looking for a multi-dimensional version of the Ramsey number, R44. So instead of just having on a square like we have on this page, you now have it on a cube, and then a 4-dimensional cube, and then a 5-dimensional cube, and much, much bigger. And he was wondering about how big does this multi-dimensional hypercube, isn't that a cool word? How big does that have to be? And so the estimate is somewhere between 6 and Graham's number, okay? So if Graham's number is about 7, then we're probably okay. Oops, session is, oh, okay, been talking too long. All right, sorry. How are we going for time, by the way? Ooh, I'm a bit over. Is everybody okay? Yeah, if you need to clear off, then, okay, it's okay. We'll laugh about you, but it's okay. So how big is Graham's number? It's a bit bigger than 7. It's a bit bigger than 8. Remember these up arrows. So this is why I introduced them before. Here we have 3 up arrow 3 is 3 to the power of 3. That's 27. Okay, 1 up arrow. So what? 3 with 2 up arrows. 3 to the 3 to the 3. We're into our power towers. It sounds like something Leonardo would be into. Okay, right. 3 to the 27. Okay, and that's this number here. Okay, that's 3 with 2 arrows. 2 arrows is that number. 3 with 3 arrows. All right, here we go. 3 with 3 arrows means take this number of 3s and put them in this power tower. Okay, yeah, exactly. That's exactly the response, okay? Take this number of 3s, which is a huge number of 3s. 7, what is that? Trillion, 625 billion, 597 million, 484, 987. Oh, I've actually got that. Okay, good. So, take that many 3s. Oh, did I mess it up? Oh. Okay, right. It was ramble, okay. Sounds like my wife's talking. Okay, so, I'm rambling all the time. 3 to the, with 4 arrows. That means take this many 3s and build this tower. Okay, now it's just getting ridiculous, so let's just get to the point. Graham's number. Here's Graham's number. take this many number of arrows, make that many arrows. Okay? Is everybody kind of on board? Okay, you want this ridiculously, well, no, this is a pretty okay number. You want that number of 3s, that'll give you that. You've got to do that one more time, okay, to build this thing. Make that many arrows, and we have just gotten started. Take that many arrows and put that in, okay? We're still nowhere near there. Do that 62 times. And that's Graham's number. The last digit is 7. We know that. So anyway, thanks for coming. That is Graham's number.
Zero.
I expect us all to sing along.
1, 2, 3, 4, 5.
All right, so yeah, thanks for coming. So that was Science Week, Science Festival. So thanks to our sponsors, University of Melbourne, the Science Festival, and ASAM's Australian Research Council, Centre of Excellence for Mathematical and Statistical Frontiers. Thanks for coming. If you've got any questions, come down. I'll be hanging around for a bit. Or we can just have a sing-along.